So that should be everything.
All right, good afternoon, everybody. So today we're pleased to have Tony Gherghetta from the University of Minnesota talk to us about HEPEC axion and the interpretation of the.
Well, thank you very much. And thanks for the opportunity to give this talk. It's a real pleasure to be here. It's my first time and really like to do it in a very nice environment. So today I want to tell you about a holographic view of the QCD axion. And this is just going to give you a different perspective of things that maybe we know from the QCD axion.
Not working, just click the screen with the trackpad. Your laptop. And that's
Once, yeah. Thank you. So let me first start with just the strong CP problem. Of course, for this audience, I don't really have to go into too much detail, but at least I can, we can see my notation. So the strong CP problem is the addition of this CP odd term in the standard model Lagrangian. And this is the theta parameter, but it also gets, there's also a contribution from the quark masses, which gives you a basis independent phase, which is theta bar. So this is a new parameter in the standard model, and this parameter can be determined from the neutron electric dipole moment. And from the upper bound, you can see that the neutron electric dipole moment depends linearly on theta bar, and then from the experimental upper bound, we haven't seen a neutron electric dipole moment, we get that theta bar is a very small number, and that's the strong CP problem. So it's been known for a very long time, and you might ask, what's the explanation for this small parameter? Now, one possibility is that you might say that in this day and age, you might say that maybe theta bar is anthropic. And you can say, well, what would happen if theta bar were made much, much larger than 10 to the minus 10? Would you actually get our observable universe? And it turns out that theta bar is actually not anthropic. It's unlike the Higgs vev, right, or the cosmological constant. Cosmological constant is the famous Weinberg bound, where if you make the cosmological constant too big, you don't get our universe. And similarly for the Higgs vev, there's a narrow window there. But theta bar doesn't appear to be anthropic. In fact, you can push theta bar all the way up to 0.1, and it doesn't really change the binding energies. I think it changes the deuteron binding energy by about 1%, and that's about it. So it doesn't appear to be anthropic, so therefore it's screaming for a dynamical solution. And so that dynamical solution that I want to concentrate on today is the PQ mechanism and the axion. Again, been very well studied. So the axion is, we're going to introduce a pseudo-scalar field, which is part of this complex field. And we're going to introduce a U1 Peccei-Quinn symmetry. And this Peccei-Quinn symmetry will be spontaneously broken, but famously it will be anomalous. And the reason why it has to be anomalous is because from the anomalous transformation of fermions, you can then transfer the axion into the GG tilde term in the QCD Lagrangian. That's the reason for it being anomalous. And it's spontaneously broken, so you would expect this mode to be massless. However, we know that the symmetry is explicitly broken by QCD effects and generates the potential for the axion. This is the famous cosine potential, although more accurately, this is an approximation to what you actually obtain, but the cosine is going to be good enough for my purposes. And then you see that the minimum of this potential, if you treat the axion as a dynamical field, it's going to relax in such a way, the minimum of this potential, such that you elegantly solve the strong CP problem. Now, in addition, you can also read off from this potential the axion mass, and the axion mass is actually determined in QCD. We know that QCD explicitly breaks the symmetry, and we can determine it because the axion, you can see it from here, you see the axion couples to QCD, this is the QCD field strength with a coupling 1 over FA, and we can compute this coupling. It's actually what's known as the topological susceptibility. You can think of the axion couples to some QCD non-perturbative physics with a coupling 1 over FA, and then this topological susceptibility is related to this two-point function involving G tilde, and that's going to give you the contribution to the axion mass. Now, later on, I'm going to come back and look at this topological susceptibility, but for now, that's why I'm going into this little detail here. And so this topological susceptibility, you can work it out in QCD from some rules, and it goes like the mass of the quarks times lambda QCD cubed. Now, the quark masses and lambda QCD, that's a constant, and so you immediately get the prediction that MA squared, FA squared is a constant, and if you plot 1 over FA and MA, you get the famous QCD prediction. So we know where the axion mass has to lie for a given coupling 1 over FA, and that's one of the nice features of the axion solution. So that's the first feature that I want to highlight. And the second feature is related to this symmetry. Now, I explicitly stated that only QCD breaks the U1 Peccei-Quinn, but there could be other UV physics that also explicitly breaks the Peccei-Quinn. And so this is referred to as the axion quality problem. And one of the ways we know that this Peccei-Quinn symmetry is a global symmetry, and we know that black holes violate global symmetries. So there could be other terms in the axion effective Lagrangian that violate the U1 Peccei-Quinn. And you say, well, what's the problem with violating the Peccei-Quinn symmetry? Well, if you violate the Peccei-Quinn symmetry, then you will misalign the potential. You'll now give another contribution to the axion which misaligns it. So here, I've shown you the axion potential. Here's the QCD contribution, and that's the one that has the minimum at the origin. But now imagine that there's another term here. You see this phi to the n term, the axion is inside the phi. This term violates the U1. You see, it's not phi dagger phi, it's just phi to the n. So this violates U1 symmetry. But this also gives a contribution to the axion potential. And I've kind of illustrated it here schematically. The dotted line, the dotted curve here is just the QCD with the minimum. But if you have another contribution to the axion potential, you could misalign the minimum. And the minimum then, theta effective, which we want to be 0, that's the effective theta term. If that's no longer 0, you spoil the strong CP solution. So that's the axion quality problem. And the way to avoid it is you just say, well, these terms have to be sufficiently suppressed that you don't destabilize the QCD potential. But unfortunately, these terms have to be suppressed to very high order. You see, this has to be phi to the 10th. And you could say, well, what happened to the phi 4th, phi cubed, phi 5th, phi 6th, phi 7th, phi 8th? Well, you just have to put it by hand. You have to say that they're not there. All right? So that's the quality problem. And this is another aspect of the Peccei-Quinn mechanism and axion solution. So therefore, with that introduction now, I'm going to ask the following questions. First of all, how do you solve the axion quality problem? Can you sufficiently suppress the higher order terms, which would also violate the Peccei-Quinn symmetry? And the second question that I want to address in this talk is, can the QCD axion mass, can it be different? And now, so let's now go back to the QCD axion mass prediction. Here I've got 1 over FA, but this 1 over FA is multiplied by alpha electromagnetic. This is the coupling of axions to photons. And the coupling to axion to photons, it's no longer a line, it's just a band, but it's essentially a prediction from QCD. And you can see here's the axion mass as a function of the axion-photon coupling, which is essentially 1/FA, as I said. But now, the question that I'm interested in is, if we change the axion mass and move off this QCD band or line, can you still solve the strong CP problem? And that would be very interesting because there's a huge worldwide effort to search for the axion. And so let's say that next week we get some kind of prediction. Someone says, oh, look, you know, I found the axion right here with this mass. And you could say, well, that's an out. But I can guarantee you that there'll be 100 papers next day on the internet saying that they've actually solved the strong CP problem. Because that's what we do as theorists. And I'm going to tell you today some of the ways that you can still solve the strong CP problem and be off the QCD line or the band. And now I'm only going to be interested in making the axion heavier. You can also entertain possibilities to make the axion lighter and still solve the strong CP problem. But those models are tuned at the moment, and we'll probably see by the end of the talk why there's a tuning there. So we don't really have reasonable models that make the axion, QCD axion lighter, but definitely you can make the QCD axion heavier. And the way I'm going to answer these questions is use the fifth dimension. So why am I interested in the fifth dimension? Well, the fifth dimension famously can, especially if it's a slice of ADS, if it's anti-de Sitter or a warped geometry, it can generate a hierarchy of scales. And furthermore, it can generate small couplings. And so here I've illustrated in this diagram here a UV brane and an infrared brane, and I'm indicating that the geometry in between these two branes is anti-de Sitter. And the anti-de Sitter allows you to generate hierarchies where K here is the curvature scale, and that's one reason to study models in this type of framework. Furthermore, from the overlap of fields in the actual bulk, the overlap between these two fields can generate small couplings. So if you need to have small couplings in your theory, you can get it from the fifth dimension. But the other reason why I like the fifth dimension is because of ADS CFT. It turns out that the warp dimension is actually dual to a 4D strongly coupled gauge theory. So when you study a model in 5-dimensional anti-de Sitter space, there is a corresponding dual interpretation precisely in 4D. So anything I tell you in 5D with the warp geometry, if you don't like warp geometry, then you can think in terms of the dual theory. And it's just a 4-dimensional strongly coupled gauge theory. So the way you can think of it is that the UV boundary, which is associated, say, with the Planck scale, you can think of that UV boundary in the fifth dimension, you can think of that as the Planck scale. And then as you move in the bulk, you actually come down in energy. So the bulk is interpreted as the 4D energy scale. And then the infrared brane is associated with some infrared scale that's associated with confinement of this strongly coupled gauge theory. So the 4D strongly coupled gauge theory, it actually mimics, you say, well, this looks exotic. Well, it's not exotic. This basically mimics QCD. Because in QCD, right, we have a cutoff on QCD, which is the Planck scale. Then when we go to low energies, we get to the QCD scale, lambda QCD. So this geometry is actually very similar to what we love and know for QCD. And we know that QCD can famously generate hierarchically small scales from the Planck scale. And this is what is referred to as the holographic view, that a 4D theory is holographically dual to this 5D antecedent. So with that background, I'm now going to introduce the problems, the axion quality problem, and I'm also going to try and address the making the QCD axion mass heavier. And I'm going to do it, first of all, by setting up the problem in a slice of ADS. So let's first of all start with the quality problem. Now, I'm only going to be giving you an overview of the idea. I don't really want to get into all the details, which I think is not the purpose here, but I'm happy to answer more questions after the talk. So what we have to do, first of all, is to just set up the quality problem. And we're going to set it up in a slice of ADS. Now, the first thing that we have to know about ADS is that there's going to be a metric, 5-dimensional metric for ADS. And the only thing you have to know about this metric is that it depends on, it comes with a curvature scale, little k. So little k will play a lot of role, will play the dimensionful, it will give all the parameters dimensions, and that's the curvature scale. So the ADS space has some curvature and its associated scale is little k. Now, I already mentioned that there's a UV brane and an infrared brane. And what we want to do, and this is the bulk here, so what we want to do is we want to introduce the axion to this geometry. And the way we can do that is introduce a scalar field in the bulk. And there's the axion. It's the angular component of this complex scalar field. Z is the 5th coordinate. So the axion does depend on Z. But other than that, that's where the axion resides. And furthermore, I want to put the Peccei-Quinn symmetry in the bulk. I'm trying to model the Peccei-Quinn global symmetry. And that, I add that symmetry in the bulk. And I'm also imagining that on the infrared brane here, this infrared brane scale, I'm going to associate that with the scale of the decay constant. And remember that the decay constant scale is roughly 10 to the 11, 10 to the 12, 10 to the 9, 10 to the 10. So it's some intermediate scale. So there's a Peccei-Quinn symmetry associated on that brane in the bulk. And then this boundary here, this represents Planck scale physics. What I'm going to do on this brane is I'm going to maximally violate the Peccei-Quinn symmetry, because that's what quantum gravity does. It violates all global symmetries maximally. So that's what I'm going to do. And in this geometry then, I now am going to solve for the profile of the axion and figure out how I'm going to solve the quality problem. Now, there's only one more parameter that I want to introduce. And when you write down the the Lagrangian for the complex scalar field phi, it comes with a mass term. So this is the mass of the bulk scalar. And the mass depends on k squared. Remember I said that k is giving dimensions always. And then this parameter out the front here, that parameter is just a dimensionless parameter, delta. Now, I've written it in a funny way, because later on we're going to see that writing this mass term is actually going to be dual to the physics in the 4D theory. But you can think of delta as just a dimensionless parameter, order 1, and it controls the bulk mass. And then you can then solve the equations of motion for this system and then analyze the breaking of the Peccei-Quinn symmetry. What's very nice in ADS is that when you solve for this profile in the bulk, it actually has 2 terms. The first term actually represents a breaking of the explicit, represents an explicit breaking of the Peccei-Quinn symmetry. And the second term represents a spontaneous breaking of the symmetry. So you can see that in this very simple slice, you have all the ingredients set up to address the quality problem. Because if you turn on this term, that corresponds to spontaneously breaking the Peccei-Quinn symmetry, which gives you the axion. If you turn on this term, this first term, that corresponds to an explicit breaking of the symmetry. And this is just a solution to a second order differential equation with these two coefficients, constants, lambda and sigma. And those coefficients, they're just determined by boundary potentials. You put boundary potentials and you can turn on lambda or sigma. If you don't want to explicitly break the symmetry by gravity, then you just turn on this term and you'll just find a massless mode. But if you want to mimic the breaking from gravity, you turn on this term and then you see what does this do to the axion potential. So let's then do that. So the first thing we're going to do is let's just imagine that we don't add any breaking from the UV boundary. So there's no explicit breaking from gravity. And so when you do that, what you want to check now is that you just have a massless axion mode. And indeed, you can solve the equations of motion. Here's the profile for the equation of motion. And what you find is you find that you do get an approximately constant profile in the bulk. And so this is the z coordinate, this is the fifth coordinate. You're going from the UV boundary to the IR boundary, and that's just the size of the profile. And you can see that remember, delta is my parameter, and changing delta just changes the profile because the integral has to be normalized to 1. And you can see that the profiles change depending on delta. And you can also check that in this limit, when lambda is 0, that you do have an axion massless mode. So that's good. So the starting point is good. That's where we want to be. And now we want to now turn on the breaking on the UV boundary. And that's going to mimic gravity maximally violating the global symmetry, the Peccei-Quinn U1. And I'm going to violate it maximally. So I'm going to add, I think we just added a linear term in phi, right? So that would be little n equals 1 from the axion quality. So I don't care. I just put the biggest breaking you can think of on the UV boundary. And then you can say, well, what happens to the axion profile when you do that? Well, that's what I'm showing here, is that the axion profile, so the dashed line, that's the case where there was no explicit breaking on the UV boundary. But if I now add some breaking on the UV boundary, what you find is the axion profile gets exponentially suppressed. So it's as if when you add a big violating term on the UV boundary, it's as if you're repelling the wave function from that boundary. And the amount of repulsion depends on the delta. So the bigger the delta, the more the profile is suppressed on the UV boundary. And so you can see then that because this model just has one free parameter, essentially one free parameter delta, you can then choose the value of delta such that you get sufficient exponential suppression to the UV boundary such that it doesn't modify the axion potential. So, of course, before I do that, when you turn on an explicit breaking on the UV boundary, that gives the axion a mass coming from the UV boundary. And again, you can see that the bigger you make delta, the more the axion mass that you get from the UV boundary is small. So that's consistent with, again, that the axion mass gets suppressed for large delta. All right, so now let's then figure out what value of delta do I need in order to solve the quality problem. So here's the axion potential. Here's the QCD contribution again. I'm now using capital F for my FA. Sorry about that. I was calling this little FA. So this is the contribution to the axion potential that just comes from QCD. But now, if you've also got another source of explicit breaking on the UV boundary, there's another cosine term there coming from the UV boundary. And this is going to misalign the minimum of A0. Remember, the minimum previously was when the argument of this cosine was 0. But if you've got another cosine here, the minimum is going to get misaligned. Now, there's two ways to solve the problem, right? So if you add another cosine term to the QCD contribution, there's two ways to solve the quality problem. The first way is to say, well, this phase here, which comes from the UV boundary, this phase is actually the same as theta bar. And if that were true, then the minimum would still be at 0. But unfortunately, there's no reason for why the phase from gravity would match theta bar. And if anybody has a way to do that, see me afterwards. Okay? But in principle, this phase does not have to be aligned with theta bar that's coming from the standard model. I think that's clear. So the only option you have is to make this amplitude very small, right? You want this cosine to dominate. If this cosine dominates, you want this cosine, if you make this amplitude very small, then this cosine won't dominate and you can still essentially preserve the minimum of the first cosine. And indeed, that's what I do here. I take this parameter that's coming from the UV boundary and I make it 10 to the minus 10 times smaller than this amplitude. And that would solve the problem. Now, when you do that, MAUV just depends on capital delta. And you can work out what you need to satisfy this equation. And you find that the critical value of delta is 10. So you need a delta to be at least 10 or bigger. And if that's the case, then this term is sufficiently suppressed, even though you've got maximal violation of the global symmetry on the UV boundary.
What's the typical value of delta you expect from it?
Good. Now, because what I was going to say, to answer your question, this seems like a bit of a cheap solution, right? Because what did I do? I added a parameter delta to my 5D Lagrangian, and then I said, well, what value of delta do I need to choose to solve the quality problem? And delta was 10. And it seems a bit cheap. However, this delta, you notice that there is a similarity with that delta and the fact that you see this little n here, it also had to be bigger than or equal to 10. I'm like, well, is that a coincidence? And the answer is it isn't. Okay, so let's now understand whether there is anything more to this model than just constraining some parameter that you put in from the beginning. Now what will happen is it'll turn out that this delta actually has. So I've given you the picture in 5D ADS, right? So now, from what I said previously, I said, well, anything that's in 5D ADS, you should be able to understand it just from 4D strongly coupled physics. And so now we have to go into the dual theory and try to interpret what does this delta mean in the dual theory. And then I think that will address your question. So for that, I need to just give you just a bit of the ADS CFT dictionary that's used in the model building with a slice of ADS. So on the 5D side, this is what I introduced on the 5D side. I actually introduced a Peccei-Quinn symmetry in the bulk. I introduced a complex scalar with a particular mass term with a particular value of delta, well, sorry, with a particular parametrization of the dimensionless coefficient in this way. I also identified the infrared scale with a warped down version of lambda UV. And that just came from the geometry. And then I introduced these two parameters, sigma and lambda. And that was the 5D toy model. What is that dual to? Well, this is the very interesting thing now, is that this symmetry in the bulk is dual to a global Peccei-Quinn. So that's what we wanted in the 4D theory. It turns out that when you parameterize the mass squared of phi in this way, this mass term is actually dual to turning on an operator of dimension delta. So delta is actually the dimension of an operator. What about the warping of the scales? Well, that's nothing other than dimensional transmutation. Because in the 4D theory, it's just like saying lambda QCD is m Planck times some running coupling. And that's how you interpret the IR scale. And then spontaneously breaking the symmetry, which is what little sigma represented, just means that this operator gets a vacuum expectation value. And lambda just means that this operator couples to some field which breaks the symmetry. And so at the end of the day, what's happening is the following, is that this 5D axion with a local Peccei-Quinn symmetry, it's actually dual to having an axion which is composite with an accidental global Peccei-Quinn symmetry. And that's how you solve the quality problem. So again, in 5D, you could add this term phi to the n, where n is just bigger than or equal to 10. But now, how does it get solved in the 4D dual theory? Well, O has dimension delta, and delta has to be 10. But now you can understand how you can get a dimension 10 operator here, right? Because this operator, it's a composite operator, it's made up of fermions. So to get a dimension 10 operator, you've got to basically have 6 fermions here. So it's a composite operator with 6 fermions. Each fermion comes with a dimension 3/2. So this would give you basically dimension 9. If you had 7 fermions, it would be dimension, so if you had 8 fermions, it would be dimension 12. So the way the 4D theory is solving the problem is it's saying that your theory only allows high dimension operators, and the high dimension operators, their dimension is determined by the constituents that operator is made of.
So that means your local symmetry is preventing any.
Exactly. And this, you say, well, seems exotic. And the answer is it's not exotic, because this is what happens in the standard model with baryon number, right? Because in the standard model, baryon number is an accidental global symmetry, and it's only violated at dimension 6. You have to have 4 fermion term. Right, in the standard model, you can write down a 4 fermion term, which is allowed by all the gauge symmetries, and it's suppressed by 1 over lambda squared. That lambda could be a very high scale, or the gut scale, or the Planck scale, but the baryon number is accidentally a global symmetry, even though it gets violated up at the Planck scale or the gut scale. Now there it's a 4 fermion term, and all we're saying here is that to solve the axion quality problem, you need at least a 6 fermion term or an 8 fermion term. So it's a little bit more than what we require, than what happens in the standard model. But nevertheless, that's how it's working in the dual picture. So this n, which from the low energy point of view, you don't know where the n comes from, you can understand it if this operator where the axion is residing in is a composite, and it's an accidental symmetry.
So are we also saying that the delta has to be greater than or equal to 4, or can I take like that? Because like if I take my delta to be like 2, like my m square term will become negative.
Yeah.
And suppose if my theory also has like a phi dagger phi square term.
Yeah.
And that will mean that like I will have to be careful with how my
Right.
symmetry.
It turns out that, remember that this delta here, that its range is actually bigger than -4. Because what ends up happening is that this delta here, this is ADS. So the mass squared can actually be negative. So you can check that in ADS with a negative mass term doesn't destabilize ADS. So you have to look at the fluctuations. It's because the geometry is curved. So there's a famous bound called the Breeton-Lerner-Friedman bound, which says that the mass squared has to be bigger than -4 to have stable ADS. So you can have delta be less than 0. Sorry, that this mass squared be less than 0, and actually that corresponds to taking delta. You see, if delta is an operator dimension, you could go all the way down to 1, actually. And indeed, you can do that. But here, we're going to be interested in, to solve the quality problem, the delta has to be very large. Has to be delta of 10, which says that your dual composite theory has to have constituents which can only form an operator which violates the Peccei-Quinn to very high order. So that's how it works in the 4D. I think it's a very nice duality here where you can see how the axion quality problem is solved. And at the end of the day, it's not that mysterious what's happening here. So now the next question is, well, okay, fine, but can you come up with a gauge theory which confines and makes a very high dimension operator which violates Peccei-Quinn? Now, when we wrote our paper, we didn't realize that people had actually written down models which did that. So now obviously that clock is not correct. Oh, 1:10, yeah, I've got to move on. But let me just quickly give you a 4D model. And then we also looked at it more recently with Peter Cox and my student on Paul. So the 4D model, so what you're interested in doing here is adding constituents, adding a strongly coupled gauge theory with constituents such that when the constituents confine, they give for you a composite axion, and they also have operators at very high dimension. And it turns out that the model that was written down by these authors, Gherghetta, Ibe, Quiles, and Gherghetta, is they introduced a new strong gauge group, SU5, with a 5 bar and a 10. And these were the constituent fermions. I'm going to be very quick here. I'm not expecting go into all the details. Apologize for that. But just to give you a flavor that you can do it. And this is a chiral gauge. This is a chiral gauge theory, SU5. And then for people that are familiar with grain unification, there's a B minus L symmetry, and that's what they identified with the Peccei-Quinn, the global symmetry. And this particular model, the first operator, well, first of all, there's a chiral condensate, so you have to make gauge invariance out of the 5 bar and the 10. So this is a 4 fermion term that you can. And this is a chiral condensate. And what this does, this chiral condensate, it spontaneously breaks this global symmetry such that you end up getting a composite axion. So that's kind of the first requirement. Exactly, yeah. Because it's anomaly free with respect to the SU5, that's right, but then the QCD has its own anomaly, yeah. Yeah, indeed. Now, you can say, well, what's the first condensate that I can write down which has a non-zero Peccei-Quinn charge? And it's this 6 fermion term here. You see, you can't write down lower order gauge invariance because the gauge symmetry, this gauge symmetry just doesn't allow you to write it. So the first term that you can write down is in fact dimension. It's a 6 fermion term. and it's dimension 9. And when this dimension 9 when this dimension 9 operator turns on, that's when you'll generate a potential for the axion. So again, what's going to happen is that any violation of the global symmetry is going to happen at very high order. Now, dimension 9 is just a bit below what you need. I mean, we need a dimension 10, but this at least shows you that you can get close. What we also did is that this same strong dynamics, it can also give you states which are neutral under the Peccei-Quinn. These are bound states, and you can actually associate those with sterile neutrinos. So what we ended up finding is that you can have a common origin for the seesaw mass scale and the Peccei-Quinn scales coming from one strong dynamics. And that was where you can actually relate the neutrino masses to the axion mass. If the decay constant and the Majorana mass for the right-handed neutrino, if they're coming from the same dynamics, all those scales are related. So this just gives you an example of a model in 4D that was motivated from the dual ADS CFT correspondence. All right, that's the first part of my talk. And of course, I don't want to say much more about this, but what you can also do, I'll just be brief here, is that once you've set up the toy model, so you notice that here's the toy model here, there's the Peccei-Quinn, IR, breaking, solving the quality problem. Once you have that framework that you can solve the quality problem, you can then solve other problems. And that's what we did here, is that we also used the bulk to not only solve the quality problem, but also explain the Yukawa coupling hierarchy in the standard model. So you actually connect the Yukawa coupling hierarchy solution with the quality problem. And what ends up happening is that you have an overlap. You end up predicting what the axion-fermion couplings are, because you see, if the axion profile is fixed to solve the quality problem, you can also fix the fermion profiles to get the right Yukawa couplings. So therefore, if you've got the axion coupling is fixed, and if the fermion coupling profiles are also fixed, the overlap is fixed, you get predictions for the axion-fermion couplings. And so that's what this is all about. And you end up getting predictions for instance, flavor violating couplings to the axions, which can determine the decay constant for coming from this particular decay of the kaon. And so this is a very constraining model, which tells you what you would need to get the right Yukawa couplings and solve the quality problem. And right now, the limits from experiment can only probe delta up to 6, but we need to get to delta of 10. Sorry, I was a bit brief on that, but let me then just move on to my second point in the last 15 minutes. So that was the first point, first topic, where I wanted to show you how you go about solving the quality problem. Now the next point I want to address is how can you generate an axion mass that deviates from the QCD prediction while still solving strong CP. So the idea there is we're going to rely on something called small instantons. So let me elaborate on that. Remember that the axion mass is related to this topological susceptibility. So that you have to work out this 2-point function. Now, you can't work it out from first principles because QCD is non-perturbative, and typically this is related to the hadron spectrum. And that's where you get this famous prediction with the coming from the pions. It's basically related to this topological susceptibility. But to get an intuition, the physical intuition of this topological susceptibility, you can approximate it with a dilute instanton gas approximation. Now, I do realize that there's people that are not familiar with instantons. This is a loaded topic here. I won't be able to go obviously too much into it, but for now, just trust me that the topological susceptibility in terms of instanton is related to this integral that you have to do. Rho is an instanton size. Instantons have a size, but they depend exponentially. This is the important point. This topological susceptibility depends exponentially on 2 pi over the QCD coupling. So alpha S here, that's just the strong coupling in QCD. Now, if you want to get a big contribution to the topological susceptibility, you see that you want to make this exponent as big as possible. And that means that you want to go to places where the strong coupling is as large as possible. And indeed, that's what happens, is that QCD coupling famously becomes strong in the infrared, and the coupling then becomes very large, and it makes this exponent very small. And if that exponent is very small, you get most of the contribution to the topological susceptibility comes from infrared scales, which is lambda QCD. And that's how you can argue that because QCD is asymptotically free, you get most of the contribution from the infrared. And that then gives you this prediction coming from QCD when you do it more accurately and relate it to the hadron mass spectrum. So that's just kind of a qualitative argument. You get the dominant contribution to the topological susceptibility from places where the QCD coupling is very large. And let me not say anything about this. This is just more detail that we won't need. Well, now you can see how to make the axion, QCD axion mass different. We need to find another place where the coupling is large. You say, well, what do you mean? QCD is asymptotically free. Yes, but we've only measured the coupling up to 100 GeV, right? So what you have to do is you have to speculate that the coupling QCD actually becomes strong again in the UV. So we want to change the coupling in the UV. So we want another place where the coupling becomes order 1. And you have to go to very high energies or small distances. And that's where you get the name small instantons. You're probing couplings now at very high energies. And so when you do that, not only do you get the QCD contribution coming from low energies, you also get a new contribution coming from high energies where you're speculating that the QCD coupling is strong again. And again, you can use the 5th dimension to do that, because the 5th dimension is famously makes the coupling strong again in the UV. And so as a warm-up, one can look first of all at QCD in flat space. So you can just put the axion, put it in flat space, and then just work out what happens to the QCD coupling when you do that. And when you do that, this is what happens to the QCD coupling. You see, here's the QCD coupling, which is growing weaker and weaker in the infrared. Now then at some point, it's becoming weaker in the UV. Then at some high scale, you start seeing the 5th dimension. What the 5th dimension does, it actually makes the coupling grow again. So if you were to speculate that QCD propagates in 5 dimensions at high energies, you would actually get another region where the coupling is large, and so you would get another contribution to the axion mass. And that's basically the idea of changing the QCD axion mass prediction. And so now one can use the dilute instanton gas to estimate the topological susceptibility. And what you end up finding is that for a 5-dimensional flat space, you end up getting this power law term Capital R is the size of the fifth dimension divided by rho is the instanton size. And this term, which comes from the five-dimensional modes, Glues-Klein and fluctuations, it actually has a negative sign, which you see, this is the usual QCD contribution, where alpha, remember alpha is becoming very small in the UV. So alpha is a small number, the action is really big. And so e to the minus action is a very small suppression. But if you've got a new contribution coming from 5D with this sign, you can cancel the big action and get a small action, and therefore get another contribution to the topological susceptibility. So that's what's happened. So you can check, you can look at the parameters and get the right, see what you get. And then this is just the result here. And the result is as follows. So what I'm plotting here is the axion mass compared to QCD, that ratio. And this axion mass is the axion mass with 5D small instantons. And we want this ratio to be bigger than 1. And that means you're enhancing the axion mass. And then this is a function of where the extra dimension appears. So see that it starts at 10 TeV. We haven't probed anything beyond 10 TeV. So there could be a fifth dimension at 10 TeV, all the way up to, very high energies. And you can see that there's all this parameter region in here where you can enhance the axion mass by factors of 10 to the 12th. Now up here, the model breaks down because you end up going into strong coupling, but down here, you can definitely get enhancement factors of 10 to the 12. So a typical axion, QCD axion is 10 to the minus 6 EV with a 10 to the 12 enhancement gets you up to MeV. And you can still solve the strong CP problem. Let's see. Notice that in principle, you could go all the way up to the string scale and you could get even bigger enhancements. But eventually, what ends up happening is that if you start turning on small instantons, you actually enhance other higher dimension operators, which also violate CP. So you have to be careful. In other words, you can't go too crazy. Now, there's another famous higher dimension term. This is another Weinberg operator. So this is a Weinberg operator. It's in the standard model, right? It's G, G, G tilde. It's dimension 6. If you enhance small instantons, you also enhance this operator, and this can also lead to large contributions to the neutron electric dipole moment. So you can't go too big in the enhancement of the axion mass, and that's what this region here means. And the discussion of that is what I have on this slide. You end up enhancing the EDMs, but we can't enhance the EDMs too much because we know that they're very small. So that's what this means here. So let me just wrap it up here by just telling you what happens in ADS. So the warm-up exercise I was doing in flat space. So what happens if you go to ADS? Well, the story actually is very interesting. And let me just briefly, just in the last 5 minutes, just tell you what's going to happen. So again, here's our topological susceptibility, which is estimated using the dilute instant gas approximation. And remember that we're always interested in this exponential, and we're interested in making the QCD coupling big in the UV. Now, whether you put QCD in flat space or warp space, the coupling grows. So you could say, well, let me construct a model in warp space and also see if I can also enhance the axion mass. And that's what I'm showing here, because it's known that the coupling, even in ADS, also grows in the infrared. Now, there are some differences. It turns out that the coupling in ADS 5, it actually only grows logarithmically. It doesn't grow power law, but that's just a detail. Now you can ask, well, can you then use this coupling here to enhance the axion mass? And it turns out that the answer is no. Surprisingly, in ADS, even though the coupling rises, you are not going to be able to enhance the axion mass because this enhancement, it has to correspond in the bulk to an instanton configuration that matches the running. And the instanton configuration that would match the enhancement of the axion mass, you can argue just doesn't exist. So it's kind of unexpected. This is just showing you the possible axion configuration, the instanton configuration that you have in ADS. You can take the instanton solution, work out the action in ADS, and you end up getting this action which depends on the infrared scale, whereas in order to enhance the mass, you needed the action to actually depend on the scale of the instanton. In other words, to have a localized instanton. The point is that this action here corresponds to instanton which is constant in the bulk. Now, if the instanton is constant in the bulk, the profile is constant in the bulk, when you compute the action of this instanton, you're going to get a very large action. And having a very large action, remember, it's exponentially suppressed, e to the minus s. S is the action. So what you really are looking for is you would want to try and find a localized instanton configuration. Because if you have a localized instanton configuration, then the integral of that localized instanton configuration over the instanton size would give you a very small action. But it turns out that you can't find localized instanton configurations in ADS, and that's a bit of a surprise. So you can also understand it from the dual interpretation, but let me not do that because I've kind of run out of time, and I've run out of time. You can also understand why this happens in the dual theory, and interestingly, the reason why it happens is because the dual theory has to have fermions, constituents. And fermion constituents are well known to give you a chiral suppression in the instanton calculation. So this is a well-known result. If you have a strongly coupled gauge theory with fermions, if you have fermions in your gauge theory, it actually suppresses, gives you an extra suppression coming from the fermion zero modes. Whereas if the CFT just had spin zero constituents, then you should have a localized configuration, as I was saying before, but you can argue that this configuration is impossible because you can use topological charge conservation to show that that configuration never is possible. So this is interesting. It basically is telling you that the CFT has to have fermion constituents, which is a bit of a surprise from the low energy point of view. Now we're also trying to avoid this conclusion by maybe doing more doing something that's called constrained instantons, but let me just leave it at that for now. All right. I should also mention that there would be other ways to enhance the axion mass. We're not the first to do it. Actually, the idea started in the early 80s. By having a strong QCD, you can enlarge QCD, or you can have a mirror QCD. These are all ways to make the axion mass heavier, but still solve the strong CP problem. And I think the message here is it's very interesting. All these ALP searches, as I said, if someone were to measure an ALP like I said, everybody would then immediately speculate that you can still solve the strong CP problem because the mass would tell you something about the UV completion or how you would have to change the running of QCD. So here are some further questions for future work. You could actually generalize this for dark matter ALPS. You could also do different versions of the axion quality problem. And then, as I said, it's also interesting to construct models in the warp space as well. So let me then end. So here's my summary. I've shown that the axion quality problem, you can solve it in the warp dimension. You see that it's just this repulsion of the wave function, the axion wave function. And that's dual to having a composite axion with an accidental symmetry. That's the mechanism. You can then use this framework then to do other things. You can explain the mass hierarchy. You can predict flavor violating axion-fermion couplings. I didn't have time to talk about the fact that you can also have light sterile neutrinos. And then in the second part, I showed you that you can turn on small instantons. They can have a sizable effect if you change the running of the QCD coupling. And then this gives you a way to probe, a way to enhance the axion mass and not spoil the strong CP problem. But the message again here is that this holographic view, it kind of gives you a complete framework to study all these questions about the QCD axion. Thank you very much.
Any questions for Tony?
So like if I increase the number of flavors, will that, because I should naively change my S effect, like the S effective value.
Yeah.
So can then that also answer your like this enhancement? Like how does that depend? Like if I just take large NF.
It doesn't, in terms of the axion mass enhancement.
Yeah.
So it turns out that doesn't, what ends up happening is that there are two contributions that depend on NCFT, the large N, and they end up actually canceling. So that's what ends up happening in this model. But however, you do need large N in order for the gravitational description to be valid. And typically, the values of N that you need have to be at least 5 or larger. But in terms of the actual enhancement, it doesn't affect it because there is no enhancement. It ends up canceling. You see, that's the surprising thing. I mean, I didn't show you all the details, but the contribution to the running is cancelled by a contribution coming from fermion 0 modes. Those both depend on N, and they just end up cancelling. Which is, again, a surprise. But it's not a surprise if you follow the topological argument of why you can't have a localized stuff. So this was a surprising, but it was a subtle point, and it was a surprising for us when we first discovered it.
So I think your DFSG axion, I
yes,
think that's a model dependent.
Yes, that's a model dependent thing.
Because you can also go to KSVZ by having some vector like for if you build
Exactly. That's true. Yes, sorry, I didn't say that here. Yes.
That's right.
That's right. This is a DFSZ model here because I'm not doing KSVZ, and indeed you can also do KSVZ. The reason why we did this is because
you had that fermion hierarchy inside. Like you use the Higgs to do some additional stuff there.
Exactly.
Connected it to fermion hierarchy.
Exactly. Yeah.
No, that's fine. But the DFSZ is so that means basically you can have both KSVZ and DFSZ quality. So
Exactly. Yeah. But here we chose this model because this one, the profiles, you can make them flat. The Higgs profiles, you can make them flat. And that simplifies the equations of motion, you see, because what happens here now is in the bulk, you've got you've got the axion and the Higgses, and you've got to solve the profiles. It's a very non-trivial problem with boundary conditions. But the problem is a little bit more solvable if the profiles are flat. But that's not a big deal, right? Because if you have these profiles that are flat, you just put the localization in the fermions. So you still have a flat profile overlapping with two fermion profiles that one's localized on UV, one localized on the IR. So the whole overlap integral still gives you a small U color.
So why I mentioned case VZ, because you need vector like that. But would that kind of help you to address later problem where you have instanton vectors?
So you're saying the answer is no.
Probably not, because you answered already to me.
Yeah, because you see that.
Problem, if you just add more flavors, probably it's not doing anything.
Yeah, it's not doing anything because the duality, you see, you already get the answer. Well, I think it's better here. You see, you already get the answer from the bulk. You see, the bulk is smart. You see, we didn't think the bulk was smart, but it's smart. It's actually very smart. The bulk knows what the dual theory has to be. So what do I mean by that? It's like in QCD, right? When you have the chiral Lagrangian, right? You just have hadron, right? Pions, and you don't know about the constituents, right? So in principle, the chiral Lagrangian is a low energy description of the UV where you have the quarks. But there are terms in the chiral Lagrangian which are sensitive to the number of colors, for instance. So it does have some information. And so the same thing is true here. The bulk description is like the chiral Lagrangian description. And so you think you can do anything you want in the bulk. For instance, you can find a configuration that looks like that, and indeed you can. This solves the Euclidean, this instanton configuration solves the Euclidean equations of motion. And it's non-trivial, by the way, because this is ADS. So there are some z-dependent derivatives, so it's not as if it's just a simple uplift, but it works. But then you say, let me go looking for a configuration that looks like that and solve the 5D equations of motion. It's like, no way. But you can understand it from topological arguments, you see, because this is the instanton. So you put an instanton on the UV boundary, and you give the instanton topological charge 1. So that means you just have one instanton. And then you extend the instanton into the bulk, and you want the instanton to pinch off so that, again, the action is proportional to this volume, if you like. So you'll get a small action here and enhance the mass. But if the instanton were to pinch off in the bulk, the 4-dimensional slices, you can work out the topological charge of the 4-dimensional slices. And so as you move into the bulk, you have the topological charge is 1, 1, 1, 1. And then when the instanton pinches off, all of a sudden you don't have any more instanton solution. So the topological charge goes to 0. But it's a topology. The topological charge is a charge in the 4 transverse dimensions there, and you can't change the topology. So that just means that you can't have a configuration that pinches off in the bulk. You can take an instanton in 4D. You can take an instanton in 4D and just uplift it, where the topological charge is always 1 at every value in the extra dimension. But if you wanted to take the instanton and pinch it off, well then it's not possible. So you can't add fermions, you can't, it's a bit surprising. So it suggests then that the CFT, the dual theory, must contain fermions because the fermions corresponds to this picture. This picture would correspond to scalar fields, scalar field constituents.
So the last thing you mentioned that if you want the axion to go in the other direction.
Yes.
So that's a curious case because
That's a curious case, and let me just get to a formula so we can. Yes. So you can see what you have to do to get an axion mass which is lighter. What you have to do is change this sign.
but is it
And so that way you get a cancellation. Now, they're actually the only model that I know that does it is a model by Anson Hook. And so what he does is he changes the phase of the axion such that you do end up getting a sign here. But it turns out that when you do that, in order to do that, you require, I think it's a very large number of copies of QCD. So we're talking about, I think it's 20, 30, I don't remember off the top of my head. So the model is a bit baroque, I mean, having 20 copies of QCD. And the whole point is that it just suppresses the whole contribution by powers of n, where n is the number of copies of QCD. So you need a lot of copies. That's the only kind of model that would work. But then to have a straight cancellation without having many copies of QCD, let's say you just had 2 copies, then you just have a tuning between those 2 terms. So you can do it, and the tuning can actually be smaller than 10 to the minus 10. Okay. Obviously, you don't want to tune something that's worse than the original tuning, which was 10 to the minus 10 for theta bar. But you can write down models where the tuning is 10 to the minus 5, 10 to the minus 6, and you can get a simple cancellation, and you can get the QCD axion to be a little bit lighter, just a little bit off the line. So that you can do. But a kind of natural kind of model which does that and solve the strong CP seems difficult.
Okay, so let's thank the speaker again.